Yes, so yes, uh, no, but I don't know if you're asking some basic questions, then it means that they should be answered because maybe I didn't tell something important. So. Yeah. Mhm. Let us solve this problem. Uh, uh, so e to I omega t d I. So I px dx over so on this one, right? Uh, so probably I suggested two possible approaches to this problem, and they look like this. So the first approach is that we can just find the singularities of this function. So hyperbolic cosine of x equals to 0 when x equals to I pi over 2 plus I pi n. Right? So we can just and when we approach this pole, then hyperbolic cosine. So it is x n. When we approach on this pole, then cosine of x is approximately x minus xn times hyperbolic sine of xn. So it's a first order zero of this function. So it equals to what it is e to the I pi over 2, which is I minus e to minus the opposite numbers. So in total it is I x minus xn, and also if also it changes sign when we change n. So x minus xn minus 1 to power n. And now, so the picture is the following. There is this real line, and there are the poles of hyperbolic of inverse hyperbolic cosine. And we can also notice that this hyperbolic cosine goes to 0 everywhere except a small vicinity of the real line, because so one maybe we can, so this is this computation around around pole, and another computation is that 1 over hyperbolic cosine of x is 1 over like e to 2 over real part of x plus e to the I imaginary part of x plus e to minus real part of x e to minus I imaginary part of x. So this goes to zero uh, uh, when a real part of when imaginary uh, um, uh, uh, so it goes to zero when a real part of x uh, goes to infinity. So basically, uh, if you consider, if you try to close this infinite infinite semicircle, for example, in the upper half plane, here it does not matter. It will go to zero on the circle, so, like for any angle alpha here. So we can basically transform this contour to something like this. So originally it was over the real line, but we can deform it to such contour. And then we can collapse this contour to sum of residues. It will be counterclockwise around any of these residues. Mm. Mm. And so on. So this integral in this first approach, and we can close it also in the lower half plane, it will give the same answer. So in this first approach, so on this picture of the contour, so in this first approach, this where is it better to write this? Maybe here. So the first computation, it is a sum over all the poles in the upper half plane. It means n from 0 to infinity. 2 pi I times e to the I p x xn over I times minus 1 to power n and well, that's all probably, right? So it is a sum from n, sum or from n to 0 to infinity, 2 pi minus 1 to power n e to I times p over times I pi over 2 plus I pi n. Oh, sorry, probably no. We cannot close it in the arbitrary way. We should care if p is positive or negative, and depending on this, close it in the upper half plane or in the lower half plane. So, sorry, I didn't think about this. But it does not matter. These contributions. No. I'm telling you the first approach to this integral, the most naive one. That we can just integrate, we can just compute this integral as a sum of residues, because yes, we can do the same, but just with one residue if we take a rectangle. Yes, it is true, but it is a second approach. In that case, we need to invent something, and here we can just naively take some of our residues. So let me, because here it is some trivial idea. You see some complex integral, just deform contour and take some of residues, and. Hmm. And it does not know anything about periodicity properties of this function, so it is just naive computation. There is this sum. It's an infinite sum, but it's a geometric progression. It is a sum from n equals to 0 to infinity, 2 pi minus 1 to power n e to minus pi p over 2 e to minus pi p n. So it is 2 pi e to minus pi p over 2 over 1 plus e to the minus pi p. And you see now that it is pi over a hyperbolic cosine of pi p. And so I gave this problem especially because this function is invariant under the Fourier transform up to some multiplication, and it looks kind of nice. So here we closed the contour in the upper half plane. It was for a positive p, so greater than 0. But we see that original function was symmetric, and the Fourier transform is also symmetric, so it is just the same function for any p. So the yes, you're right. Thank you. Yes. Thanks. So it's a kind of a naive approach which works in the trigonometric case, because here we can be so naive, just see the integral and compute it as a sum of residues. But there are examples, for example, when this function is doubly periodic, and we cannot compute the sum of residues because it is a double lattice. It is complicated. So in this case, in such cases, we can use periodicity properties of this function. Namely, there is a second approach. So we can consider the integral which depends on some variable a, and second approach, we can consider an integral which is I of a, and it is integral over I a plus a real line e to the I pi x dx over hyperbolic cosine of x. And what we see now, that I of 0 is just our original integral. Let us call this I. So I of 0 is just I. And compute who is I of I of pi. So on one side, we can write that it is we know that cosine of x is I pi periodic. So we can write that it is integral from minus infinity to plus infinity of cosine of x like plus I pi, but it is the same as cosine hyperbolic of x. It is periodic times e to the I pi or I p a times e to I a p I p x dx. So it is different from I of 0 only by this factor. So it so I pi p. So it is equal to I, or maybe with a minus sign. Sorry, e to the minus pi p I of 0. So it's one computation. Another computation, and that when we can consider I of 0 minus I of p, and it equals to the integral over the following contour. This contour C and goes like this. It is integral the real line, so it is 0. And then in the opposite direction. So it is I pi. And we can close it at infinity because integrand goes to 0. It is our contour C. So it is an integral of this function e to the I p x over cosine of x dx. And since there is only one pole in this domain, we can compute it as a single residue. So it is 2 pi I times residue at x equals pi over 2 of this function. So it equals to e to minus pi p over 2 maybe times 2 pi. So on one side we have this equality, on the other side we have this equality. So now let us combine this and get that. Mm, hmm? uh, where? Yes, yes. Thank you. Yeah, yes. Yes. Mm, yes. Yes. Thank you. So, yes, it's real and antiperiodic, and so this equals to minus cosine of hyperbolic cosine of x. So here we have minus sign. Thank you. So now let us substitute this equality, and we see that I of 0 minus e to the minus pi p I of 0, plus, because minus and minus, this equals to 2 pi e to the minus pi p over 2, and so we conclude that I of 0, which is our original integral, is pi over hyperbolic cosine of pi p over 2. from the same answer. And you see that this method can be applied to any function which is periodic or anti-periodic in this imaginary direction. So, um, so it's like this such a trick. So, are there any other questions? Mm, mm, so, mm. So maybe let's go back to two-dimensional Laplace equation. Right? So, so uh, mm, uh, we were solving this equation, which can be either zero or some delta function of z minus z0. Mm. Uh, and we found that it is always useful to find some conformal map of non-trivial domain which we study to something simple, either to disk or to upper half plane. So, and I would like to tell a little bit more about conformal maps. Let me check. Okay. So, let us consider, for example, these maps. So we know that the map compactified complex plane to compactified complex plane of one-to-one O. And maybe the main property that can be practically useful, the main property of this map, in that it maps circles to circles. And a straight line is also a circle, but it has infinite radius, and its center is placed at infinity. So, and it is easy to understand why it is so, because, for example, let us say that we have a circle in the image. So az minus b over z minus d minus some z0 times complex conjugate of this z minus b over z minus d minus minus 0 minus z0 complex conjugate equals to some r. Then, if it is so, then we can multiply it by the denominator and see that az minus b minus z0 times z minus d times az minus b minus z0. Because I wrote minus here and wrote it everywhere, so it's in the same. So it's better to write it in the canonical way as d. So it equals to r complex conjugate complex conjugate. And if we now open all these brackets, what will we see? We will see some number times absolute value of z squared, like maybe z bar, plus some number times z plus some number times z bar plus some other number equals to 0. And it is clear that if we write it in terms of in terms of real numbers, it will give us x squared plus y squared plus some number times x plus some number times y plus some number equals to 0. And it is, of course, the equation for a circle. And if you want to find some a conformal map of some domains which have circular or straight lines boundaries, it is enough to understand what is the map of some specific points, and then you know that if they were on a circle originally, then they are on a circle after this map. So there's some problem about this, and you can try to see how it works. So are there any questions about this? And for example, if all these A, B, C, and D are real numbers, it maps upper half plane to upper half plane, and we see that then this group is well, and we can ask the determinant to be 1. Then this group is more or less SO2R. Better to write PSO2R because they are defined after multiplication by some number. And we know that that this is a group of automorphisms of the upper half plane. And we also knew from some computation several lectures ago that there is a group of automorphisms of the unit disk. And that group was SU11. This group acted here. And since we know that unit disk and the upper half plane is the same, we know that these two groups are isomorphic. And you can write this this isomorphism explicitly if you compare the action on both domains. Is it fine? So then there is another example. There is a map Z goes to Z to some power, and let us wait. What is better to write? Let us consider the map Z to power 1 over A. So if you write it in the polar coordinates, it will map R e to the I phi to R to 1 over A e to the I phi over A. So if we act with such a map on a piece of of the upper half plane, for example, and this is point 0. We find that a real line is mapped to the real line. And this positive half line is mapped to positive half line, and this negative part is mapped to something rotated by some angle, and it is and this angle is pi over a. And for example, this can also be used not on the upper half plane, but it can be used in such a situation when we have for example, we can solve the following problem, like find a conformal map of the upper half plane with some curve removed. So let us call this variable z, and so we want to map this to just the upper half plane, and so let us call this point z0. And this point 0 maps to some point w0 on the upper half plane. So the left boundary of this cut will map to some point minus, to some point w minus, and the right half will map to some point w plus somewhere. So we can look for such map. So that it separates the boundaries of this cut and maps it to this pieces of the upper half plane. And so if I draw a kind of constant real and imaginary part lines on this picture, we can think about this, for example, about some equipotential lines, or some flow lines. Then on this picture, they will go like this. Like this. So there will be such kind of picture. And there is a nice equation which describes the situation, which I want to derive now. So this is this W plane. So we are looking for the map W of Z, which maps this upper half plane without a removed line to just upper half plane. And also it turns out that it makes sense to consider not only this map, but also consider an entire family of maps parameterized by parameter t. which looks like this. So for t equals to 0, we have just upper half plane, and for some t, then t equals to some epsilon, we have some a short piece of this line, and then for arbitrary t, we have this entire line which ends at z0 on z0 of t. And it makes sense to write a differential equation for this w. And now how it works. So let us look at a small vicinity of z0 of t. So and w of t, so it's better to switch from to w of t and z. And also we ask for asymptotic condition for this w. So of course when t equals to 0, then w of 0 and z is just identity map. We don't need to remove anything. And if and we can also say that if we are far away, then this conformal map should be asymptotically z. So w of t and z, when z goes to infinity, should behave like z plus maybe like z plus probably O of 1. No, they are in some smaller in some decaying powers of z. It means that if we are far away, then the exponential lines are not deformed, but we have some infinite series in inverse powers of z, and if we approach a position of this cut, this powers of z start to play a role and deform all these lines in some non-trivial way. But if we are far away, then this problem can be solved as a series in inverse powers of z, and this works. Such approach works even for some complement to Julia set. So people are able to compute this expansion in that case. So, but now we want to derive some differential equation which describe this w, and it goes like this. So let us look carefully at the vicinity of this point. So here we have precisely this situation that there is cut, and we want to open the boundaries of this cut. So on this local picture looks like this. We need to map this to this. This is Z0, and this is W0. So if you look at this picture, we see that if we take some angle which equals to 2 pi and take square root, we will get precisely the angle pi. So we can conclude from here that W is W of t and z is approximately a square root of some C of t z minus z 0 of t. So is it clear? Plus plus some constant times z minus z 0 of t, probably plus something else. Because this conformal map does precisely this. So we can write another picture that if we have the angle of 2 pi here, then it maps to this picture. It maps to 2 pi over a. So if you take a square root, it will map this complement to this line to a small piece of the upper half plane. And now we should say yes, but it is enough to write differential equation. So now there is an important question: what is the value of this c? So we see that there is a vector which equals to so it is a speed of this point, and it is a vector z0 dot. It's time derivative of the zero, and we see that when we substitute when we are on the boundary of this cut, namely when z equals to z0 minus epsilon z0 dot, I parameterize this way some point on this cut. It is point somewhere here. Then this expression c of t times z0 minus epsilon z0 dot minus z0 should be positive. So we can so it means that z0 dot times c of t because it is precisely those are precisely points on this branch cut, and they should map on to the real line to positive. Oh, sorry, I forgot to write a constant part of this because it is not mapped to 0. It is w0 plus this one. Sorry, it is like this. So this 0 dot times c of t is less than 0, so we can write that c of t is some probably minus b of t divided by z 0 z0 dot. And now let us try to derive an equation.
What we draw, we are excluding the horizontal line, right? So we are in the half planes. We are not considering the border of the half plane, right?
What do you mean? No, the points of this border map to the points of this border. Right. So this part maps here, this part maps here, and so this part of card maps here, and this maps to this right part. No, why? Of course, they are cut here. Like the limit from the left and the limit from the right are different.
And also, I mean the deformation we did, so that line is like split in two and put in two different parts. But each point of the line is put in 2 points on the image.
Yes, but well, maybe it's better to say that it is a map of
we consider it as a map that excludes those points from its domain, it's well closed.
Yes.
Well closed, right?
Yes, maybe better to say that it is a map for open domains, and sometimes it has a limit to some points of this real line, for example, and sometimes these limits coincide on this side and are different on this side. So. It is some positive number. So it is just nice to parameterize because we are free to choose parameterization of the zero of t, and in principle we are free to choose some rescalings of this map. So we can do like this. And now if now let us try to derive differential equation. So let us try to consider dw over dt. So it equals to so the main part is derivative of this square root. It is minus it is minus z0 dot times times c of t over 2 the square root of c of t z minus z0 of t. So this part is singular. It goes to infinity when z goes to 0. And the remaining part is all of 1. So we can now write it as so using this equality we can write it as b of t divided by 2 w minus w0 of t. And plus all of 1. Sorry, probably. No, this one is right. Of course, there should be, but it is all of 1. It does not go to infinity when z goes to the 0. It's all here. So Now we see what that um, and we are also free to choose parameterization of our curve. We are free to choose b of t equals to 1, to 4 actually. Because if we just reparameterize time, so when t goes to some f of t, b of t goes to b of t times maybe divided by f prime. So this reparameterizations allow us to fix b as constant. And when we have this, we can now uh, because it is some standard convention for this equation. Uh, because people usually write 2 in this numerator. Hmm? W is our conformal map. Uh, so, so this equation is dw of t and z over dt equals uh, to 2 over w of t and z minus w0 of t plus O of 1, right? So is it fine? W0 is an image of this point on the boundary of the upper half plane, and it depends on t. Yes, I should have written it here. Plus square root. Right? Is it? So, and we can also notice that mm, we can fix parameterization of this curve in this way, and mm, now we see the following fact that the ratio dw over dt plus minus 2 over w of t, like t and z minus w0 of t. It is a regular around w0. Second, it is a real on the real line. And it it is also homomorphic in the upper half plane because it is by construction. Mm. Uh, and also when a W goes to infinity, uh, we can so in principle our when W goes to infinity it should go to constant because we know that asymptotics of W around infinity is Z, so time derivative of W will be of order 1, and and around infinity W and Z is the same, so it is O of 1. And it is clear that if we have such a function, then it can be only constant, because and because, for example, of this relation between real and imaginary part of functions which are homomorphic in the disk or in the upper half plane. So we see that it is constant. And moreover, since our W is defined up to, so if you fix only this plus O of 1, then this W of Z is defined up to addition of some constant. And maybe it might make sense to change this condition, but we can choose this freedom. So we can also use this freedom to change W of T and Z to some W of T and Z plus some constant, probably dependent on T. Mm. And then make this function just 0. Mm. So from here we get so from here we get the equation that dw of T and Z over dt equals to 2 over W. And so this is some differential equation. And together with this condition that W of 0 and Z is Z, it defines for us this conformal map. This is called a Lovner equation. Mm. And let us consider some example, which is the simplest one. Mm. Here the only here it is some weird parameterization of the shape of this part of the complex plane. It is parameterized by time dependence of the image of it in the upper half plane. But let us consider the simplest example. Let us consider W of t is constant. W0 equals constant. So in this case, we have this equation, dw over dt is 1 over w minus w0. So, 2 over w minus w0. So, we see that d w minus w0 squared equals to 4 dt. So W minus W0 equals to W minus W0 squared equals to what? So originally we had so when t equals to 0, W equals to Z. So we have Z minus W0 squared plus 4t. Right? So a solution for this problem is W equals to W0 plus square root of Z minus W0 squared plus 4t W of Z. And now let us see how this conformal map works. So there is this upper half plane. There is somewhere point W0. Let us see. So we have this conformal. We have this conformal map. All right, and let us see what happens with the real line. So we can. So when Z is positive, maybe let us start from negative Z. Then we have approximately W is Z. So this part is mapped to let us maybe move to this blackboard. So when W is negative, we should choose this branch of square root, but we can choose it such a way that it maps to just a negative half line. So and when Z equals to just W0, we will get W0 minus square root of 4t. So this is the point, W0 minus square root of 4t. But now let us see what happens when we reach this point W0. So when Z is approximately W0, then W of Z is W0 plus square root of minus square root of 4t, and then we expand this square root, so it is Z minus W0 squared over 4t plus 1. So it is W0 minus square root of 4t minus z minus W0 squared over what, over 2 square root of so so we see that it is a map which raises z minus W0 to the second power. It means that this map, this map does like this. It maps such an angle to the piece of the upper half plane. This is the right angle. Sorry. Well, let's write it. Let me draw it like this. Mm. So it means that we precisely meet this situation. So we see this corner, 90 degrees corner, and it now becomes a straight line till W0. It means that it means that when we reach W0, this becomes 0, and now we can go to the imaginary direction. We can go along the straight line up until we meet this point when this number becomes equal to minus this one, when this square root vanishes. And this happens when z equals to W0 plus I square root of 4t. And after this, we go down. So we get on this other part of this cut, W0 plus square root of 4t, and then the remaining part of the upper half plane. So is it clear what happened? And so
If we consider the W we found for the one,
mhm.
and we see also the one that we expected to find at the start. So yes, that
Mhm.
one.
Yeah.
So which is the relation between them? Because
It's it's precisely this. This is a globally defined function, and if we expand it around z equals to if we expand it around this point, which is z0 of t, then it will be this series. So. Mm, so. Mhm. Mm. So there is some science related to this equation. For example, people consider this W0 of t to be some random variable, and can consider domains with random complex domains. But here I just wanted to show this nice example and a related conformal map. Mm. So are other questions about this? Mm. Mm. Well, so let us maybe go further and mm. so there is a so in this way we can find green functions in some domains which look like this, but there are also other problems. For example, we can consider a green function on a cylinder. So, namely, we can consider uh, uh, mm, we can say that there is such an infinite strip from 0 to 2 pi I. Mm. And we identify this part and this part. And we want to solve this equation that 4d bar of u equals to delta 2 of z bar, and also we can think about this as periodic functions. So we can ask that u of z plus 2 pi I is 0 in the same of u of z 0. Mm. And it turns out that this problem can also be solved using conformal maps, because there is an exponential map. So if you consider w, which is e to the 2 pi, which is e to z, then these lines of constant real part of z turn into lines of constant absolute value of z, and it maps like minus infinity is mapped to 0, and we have a picture like this. And then to infinity. So in this way we can reduce our problem to a problem just in the whole complex plane. And so the solution can be obtained as before. So this gain function is g of z0 is 1 over pi logarithm of the absolute value of e to z minus e to z0. But in this case, there is a small problem with this gain function because it is a bit non-symmetric. Namely, let us see what happens when z goes to plus infinity. Then this exponential dominates, and this gain function behaves like it behaves like 1 over 2 pi, 1 over 2 pi, a real part of z. And when z goes to minus infinity, it behaves like 1 over 2 pi minus a real part of z0. So this and the asymptotics of this gain function is like this. So this is maybe better to draw it this way. So it is linear in one direction and constant in the other direction. And I don't know. Does it remind you anything? Like, have you seen such an asymptotics of the gain function in any problem before? Like, uh, do you remember a solution of the Laplace equation which behaves as a constant at as constant or as linear function at plus or minus infinity? I want to say the following. So we are considering this Laplace equation on a cylinder, and so this is a trick which you can use in 2 dimensions. But in principle, if you want to find some gain function, we should use a Fourier transform, and this Fourier transform in this y direction is like this. So u of x, y can be written as sum from sum over the integer numbers u n, which depend of x, times e to the I n y. Right? If you look for functions which are periodic in this direction, and if you substitute it into the Laplace equation, then if you want to solve Laplacian of u equals to f of x and y. This turns into Like who can tell? Oh, it's Poisson equation. Who can tell which equation is satisfied by un of x?
Should it be 1 over I of absolute value of RT of Z, real part of Z?
Uh,
No,
what?
when we take the
Mhm.
absolute value of the real part.
But it's that goes to plus infinity. It's only in one limit.
Okay.
Because in this limit, this exponential is much bigger than this one, and in this limit, it goes to zero.
The other, when we that we have to minus infinity, we get minus RT of Z. Shouldn't the absolute value of RT of Z zero?
No, because it is. So let me think. You take here the logarithm of the absolute value. It can be. Well, sorry, it will be just this one without minus. Because we are taking a logarithm of the absolute value of the exponential of the zero. And the absolute value of the exponential is exponential to the real part of z, right? So, because it is so is it obvious? Because e to the zero equals to like if z is x mm, plus I y, then e to the equals to e to the x uh, times e to I y. The absolute value of this is is one, and the absolute value of this is like just this number. So, but who can tell me the equation for the mode of this u? What happens if we substitute it from the Laplace equation and say that f has the same expansion? Hmm? So we are saying that let us have an equation, Laplacian of u of x and y equals to f of x and y. And let us say, maybe for definiteness, that f of f of x and y is 0 when mm, absolute value of x is greater than L. Mm, so we want to solve this equation using the Fourier transform. f of x and y is a sum of fn of x e to the I and y, and also for u. Mm, mm. Un e to the un of x e to the I and y. And I'm asking what is the equation for components of u for UNs. So there is some equation for UNs. So who can tell this? Hmm? Yes, and what does it give? Mm-hmm. Mm-hmm. Yes, thank you. A fan of x. Uh, Thanks. Uh, and what we see now that we see that there are equations for some non-zero ends. And if you want to solve this equation, we should also ask something like un of x should go to 0 when absolute value of x goes to infinity, so that we don't get growing solutions. And we can solve this equation for other modes, like we can apply a gain function and say that so it's exercise to check that this holds, so that un of x is something like minus infinity to plus infinity, if I remember correctly. Dx dx prime e to minus n absolute value of x minus x prime over 2n probably times fn of x prime. So the exercise is to check that such formula is correct. So we can solve this equation this way for this modes. And we see the main property of all these exponentials that they decay at infinity, and the higher the mode is, the faster it decays. And but if you look at n equal to 0, we see that u0 to primes of x equals to f0 of x. And this is precisely a one-dimensional Laplace equation, or Poisson equation. And this non-symmetry, this linear growth at infinity, is precisely the signature of this one-dimensional Poisson equation. And by the way, this phenomenon is called so these exponentials are called in physics like Colescline modes. So the phenomenon is that if you consider a cylinder and take a big enough distance between different points, it will cause effectively such a phenomenon like dimensional reduction. So if one of the dimensions is compact, then gain functions for equations and that are considered on the space look at big distances, gain functions of some of the same equation in a lower dimension. So it is a kind of so in this limit, when these points are far away, it looks like a 1D Poisson equation. And when these points are close to each other, like they're very close, then it is like a 2D Poisson equation. So and we see this precisely in this formula for the green function. When z is big, and which means that it is far from z0, asymptotics of this green function is a linear or constant, precisely like in the green function of one-dimensional Poisson equation, and we see this from explicit solution. But when we go, when these points are close, we see this logarithmic logarithmic singularity, and this is what should be in 2D. So it's a kind of intuition, like to understand what should we expect when we start solving some equation. So are there any questions about this? So actually, this grand function is not very good because, for example, it is not very well defined because it's non-symmetric. In principle, we can add some linear terms like real part of z, which is also a solution, but so there is this problem at infinity. But we can consider a little bit better problem. Namely, we can now consider this Laplace equation not on the cylinder, but on the infinite strip. Namely, let's say that there are such boundaries it is 2 pi I, it is 0, and we say that and that we are looking for a solution for question of z0 equals to the dimensional delta function of z minus z0 with boundary conditions, like g of z0 equals to 0 when z is either on the real line or z is on 2 pi I plus real line. And or maybe it's better to put here just pi I. Yes, better to put here pi I. So, and idea of a solution of this problem is the following. So, let us consider a cylinder from from minus pi I to pi I, and let us say that there is a charge at point 0, and let us add. So this is a charge this sign plus 1, and put another charge at point 0 bar minus 1. And we see that if we go to the real line, then potential created by these charges should be 0. And because of symmetry, this potential should also be 0 on these lines. So if we have precisely satisfied these boundary conditions, so the answer for the gain function is g of z0 is 1 over 2 pi logarithm of the absolute value e of z minus e of z0, e of z minus e of z0 bar. So maybe the only thing we could check is on this gain function on the real line. So when z is on the real line, we want to compute. So we can write it like absolute value of z minus absolute value of z0 over absolute value of z bar, because it is real, so conjugate is the same, e to z0 bar. Those numbers are conjugated to each other, so their absolute value is the same, and the absolute value of this is 1, therefore. And we also notice that if z is in pi r, pi I plus r, this exponential will also be real, but negative. So this also applies for z in pi I plus r. So that's all. So this gain function is 0 on the boundary. And we see that in this case there is no such problem with asymptotics of this gain function. It is not growing, because if we impose zero boundary conditions on this strip, then this zero mode is absent in the Fourier expansion, and we have only decaying exponentials as it should be. So this gain function behaves like so when a real part of z goes to infinity, well, just z goes to plus infinity, this gain function behaves like 1 over 2 pi logarithm of 1 minus e to z0 minus z over 1 minus e to z0 bar minus z. So So logarithm of 1 plus absolute value, logarithm of 1 plus z absolute value is 1/2 of logarithm of 1 plus z plus logarithm of 1 plus z bar, and it equals to the real part of z plus something. So synthetic of this expression is 1 over 2 pi 2 pi real part of e to 0 bar minus z minus e to z 0 z0 minus z. So we say that the Sangren function goes to 0 as it should be, and it is consistent with this asymptotics, which we can find using Fourier modes on the circle. So there is such an answer. So are there any questions about this? Okay, can we go further? Mm, what do you mean? Like, what kind of problem? Ah, but for example, a Lagrange function is um, kind of basic, like a starting point for one of the approaches for this domain. So mm, so there is such problem, and one of the approaches is to say that it is this infinite strip with a imaginary charge minus 0 um, minus 0 bar. And another approach is to check that this function hyperbolic sine of z actually maps this domain to the upper half plane. So, but try to solve that problems, and if it is unclear how to do this, we can solve them during the lecture. So, let's end. Hmm? Oh, so no, not yet. I saw some instruction about this, but I have not checked what are the possibilities. So probably I will write you an email asking about restrictions, preferences, and so on. So or maybe asking next time. So. Ah, so So this was a grand function on the cylinder, but there is also another uh, mm, another important problem, namely the grand function on a torus. And theta functions. So the problem which we want to solve is the following one. So there is a domain in the complex plane of this shape. It is a parallelogram. Uh, this is 0. This is a tau. This is 1 plus tau. And we identify this side of this parallelogram. So topologically it is torus. So maybe I'll just tell the definition today, and we'll study some properties of this all these functions the next time. So we want to solve the following problem. So we want to find again a grand function of the Laplace operator. So let us first write something for the bar g equals to delta 2 of z minus z0. And we also want to have that this function is periodic. G of z plus 1 and 0 is g of z, z0. And g of z plus tau, z0, equals to g of z, z0. So there is a problem which we saw at the very beginning, that if you try to solve this equation, then it is impossible, because there is a restriction that integral of Laplacian over some compact surface is 0. So the integral of the right hand side should also be 0, which means that we can consider only functions with 0 integral. And when we work on the space of such functions, we can also put the right hand side to the space by subtracting the following number: 1 over imaginary part of tau. Because you see, the area of this parallelogram is precisely an imaginary part of tau, because it is, and this is 1. So the area is the area of this rectangle. So if you subtract this, then there is a chance to solve such equation. And but before thinking about this, let us try to write some function which is which has some nice periodicity properties and has 0 at 0. So, namely, consider the following series. Better to try this way. Pi tau, sorry, times this expression. So it's by definition. So you see that this series is variable convergent because imaginary part of tau is greater than 0. So it decays like e to something times e to minus something times n squared. So it converges super fast. So the first property which we see immediately is that when z is 0, this series has a symmetry n to something like minus 1 minus n. It vanishes.
So we have pi I tau, which is
Yes.
and then pi
N plus 1/2 z. So the first property is that tau 1 of 0 tau is 0. So second property is actually just a generalization of this one, that tau 1 of minus z tau is minus theta 1 of z tau. So it's odd function of z. And the last property, which maybe it is better to study the next time, because the time is almost over, that if we consider theta 1 of so I forgot about this property. So this function is anti-periodic. Z plus 1 tau is minus theta 1 of z tau. And the last property, which is essential, that theta 1 of z plus tau is actually I forgot precise number, but it is something like e to the minus 2 pi I z, maybe e to the minus pi I tau. I forgot precise factor, but it is of this kind times theta 1 of z tau. So these two properties together with this one, that it is that at 0 it equals to 0, says that we constructed a function which has zeros at all these points of two-dimensional lattice. And it is almost periodic. So we need to solve some extra property to modify it a little bit, so it becomes just a periodic function. And then we can just take a logarithm of the absolute value of theta 1 of z minus z0, and it will be a grand function on a torus. And so we will do this next time. And it also turns out that this function, to be precise, some slight modification of it, also gives a grand function of the heat equation on a circle. So maybe I don't know if there is any deep meaning of this coincidence, but this also describes that other problem. Because it is a sum is a sum of minus 1 to n e to the phi I tau n plus 1/2. So we can write that it is basically sum over z n some k is in half integer numbers, 1/2 plus z. And here it is k squared, and here is minus 1 to k. And we have this symmetry, k to minus k. So here we have 1/2, 3/2, minus 1/2, minus 3/2. So we have the symmetry which exchanges them. And this term stays constant, but this minus 1 to k always changes sign. So everything cancels because of this. Or it can follow from this property as well. So are there any other questions on this? Okay, then thanks for your attention. See you next time.